Hello everyone. Today we are entering into the session 8 of the chapter Moving Charges and Magnetism. So before entering into the topic, I am going to discuss these things first. First of all, the Fleming's left hand rule. Let us recall the Fleming's left hand rule from our previous session. So what does the Fleming's left hand rule says? Stretch the thumb, forefinger and middle finger of your left hand mutually perpendicular to each other. Then your middle finger directs in the direction of the current. That is, it is going to indicate the direction of the current, and your forefinger indicates the direction of the magnetic field, whereas your thumb indicates the direction of the force. This is what the Fleming's left hand rule says. Next, what will be the force on the current carrying conductor which is placed in a magnetic field? Now, if I place a current carrying conductor in a magnetic field, then this current carrying conductor experiences a force, and what the force is given by? It is given by the formula IL cross B, or you can also write this formula as ILB sin theta, where I is the current in the conductor, L is the length of the conductor, B is the magnetic field applied, and theta is the angle between the length vector and the magnetic field. So this is what the force on a current carrying conductor which is placed in a magnetic field. Now let us discuss torque and couple, which you have already studied in your first PUC. Now let us recall, the torque is nothing but it's a force which causes the object to rotate about an axis. Now if I have a book or an object something like this, so I am applying force on this side of the book in the downward direction and in the upward direction on this side. That means whenever you apply forces which are anti-parallel to each other, the force here is acting downward and the force here is acting upward. They are anti-parallel to each other. That means they are equal in magnitude but they are opposite in direction, and they are acting on the different points of the object. Like on this book, the forces are acting on different points and the line of action is same. They are acting on the same line of action but on the different points, and they are anti-parallel. In this case, the book is going to rotate. These two forces which are acting anti-parallel are going to form a couple and make the book to rotate. That is, now it creates a torque. Next, coming to magnetic moment. I have already explained you, a current carrying loop acts like a magnet. It acts just like a magnet. If I have a current carrying loop, and here you can see the direction of current is clockwise. Whenever the direction of current is clockwise, then this side of the current carrying loop is considered as the south pole. And whenever the current is flowing in the anti-clockwise direction, then I am going to consider this side of the loop as north pole. So a current carrying loop is going to act just like a magnet with two poles, that is dipole. One side, which is where the current is flowing clockwise, will be acting as a south pole, and the other side where the current is flowing in the anti-clockwise direction is going to be a north pole. So since a current carrying loop acts like a dipole or a magnet, I can say that the magnetic moment is denoted by the letter M, and this M will be equal to the current in the loop into the area of the loop. So this M is nothing but the dipole moment, magnetic dipole moment or magnetic moment, and it is denoted by the letter M, which is equal to I into A. Now how to find the direction of the dipole moment? If I have to find the direction of the dipole moment, just curl your fingers in the direction of the current and your thumb indicates the direction of the dipole moment. So in this case, the dipole moment direction will be outwards. It is perpendicular to the plane of the paper, always perpendicular, and it is outwards, and in this case it is inwards. Always the dipole moment will be acting perpendicular, but in what direction? Is it out or in? For that you have to look at the direction of the current. So if the direction of the current is this way, then the dipole moment will be outwards, and if the direction of current is this way, then the dipole moment will be inward. So the topic I am going to discuss today is the torque on a rectangular current loop placed in a uniform magnetic field. So I have this rectangular current loop. So you can see A, B, C, D is a rectangular current loop. So this rectangle is having length A. Let me say its length is taken to be A and the breadth as B. So this is the rectangular loop which is connected to a battery. Then the current is flowing in this rectangular loop in this direction, that is from A to B to C then to D. This is how the direction of current is, which has been represented using a arrow mark. Now this rectangular loop is placed in a magnetic field. You can see I have placed the north pole of the magnet and south pole of the magnet here. So the rectangular loop is placed in a magnetic field B, and the magnetic field is in this direction. This is what the direction of the magnetic field is, that is from the north to south pole. Next, let us write the direction of the dipole moment. As you know, this loop is going to act as a magnet, and its dipole moment direction will be, curl your fingers in the direction of the current, then your thumb indicates the direction of the magnetic dipole moment, and it is inwards. If I say that this plane is something like this, that is, if this is the rectangular loop, so I have placed it in this direction, then what will be the direction of the magnetic dipole moment? If you just curl in the direction of the current and see, it is downwards, it is acting downwards. Therefore, the magnetic dipole moment will be acting downwards. Now, I am considering the case 1 where the magnetic field will be along the plane of the loop. So in this case, if this is the plane of the loop, then this plane of the loop is placed along the magnetic field. So the magnetic field direction and the plane of the loop are in the same direction. That is, if this is the plane of the loop, then this will be the direction of the magnetic field, or the magnetic field will be along the plane of the loop, is what the condition we have taken in the first case. Now let us see what will be the force on all the sides of this rectangular loop. Now considering the side AD. AD is the side which is having length A. AD and BC are having length A, and the force on these sides will be equal to, F is equal to I B L sin theta. This is the formula. Let us use this to in this case, in this rectangular loop, I is the current in this rectangular loop, B is the magnetic field. Coming to the length of both AD and BC is A, therefore I am going to write this as A sin. What is theta? So coming to AD, in case of AD, the direction of current is this, from D to A, and the magnetic field is applied along this rectangular loop, plane of the rectangular loop. Therefore, if AD, the current in the AD is in this direction and the magnetic field is applied in this direction, what is the angle between them? It is 180 degree. In case of AD, the force will be equal to 0, as sin 180 is 0. Coming to the side BC, what happens to the side BC? F is equal to, similarly, IB A sin. Here you can see the current is in this direction and the magnetic field is also in the same direction. Then the angle theta will be equal to 0 degree. Therefore, again the force is 0. Therefore, no need to worry about the sides AD and BC here, because in case of AD, the magnetic field is making 180 degree with the length element, and in case of BC, the magnetic field is making angle 0 with the length element. Therefore, the force on these two AD and BC, these two sides will be 0. Now let us see what will be the force on AB and CD. The force acting on the side AB and CD due to the uniform magnetic field will be written as, let me say, the force on the arm AB, this A to B, the force on this arm AB is taken as F1 and it is equal to I, B, B, because this side is taken as B, into sine. What is the angle between the magnetic field and the length element? Now, this is AB. The magnetic field is somewhat like this. Now, can you guess the angle between the magnetic field and this length element? They both are perpendicular to each other. The length element and the magnetic field are perpendicular to each other, because the magnetic field is in this direction. It is perpendicular to this length element. Therefore, this is 90 degree. Now this F1 will be equal to IBB, sine 90 is 1, therefore this is F1. Similarly, let us find the force on the arm CD. The current is flowing from C to D. What is the force on this? I am going to consider the force on this arm CD as F2, and that is equal to IBB, same, the side is same. Coming to the angle, here it's the same, because the length element is in this direction and the magnetic field is acting like this. That means they are acting perpendicular to each other. Therefore, this is sine 90. Sine 90 is equal to 1. F2 is equal to IBB. You can observe one thing here. The forces F1 and F2 are equal in magnitude. IBB and IBB, they both are equal in magnitude. But what about the direction? Let us check what will be the direction using Fleming's left hand rule. Now stretch the thumb, forefinger and middle finger of your left hand mutually perpendicular to each other. Your middle finger represents the direction of the current. So first I am going to place the middle finger in the direction of the current, and forefinger represents the direction of the magnetic field. So if this is the direction of current, this is the direction of magnetic field. What about the force? The force is something like this, that is inward. Next, coming to the force in the case of the side arm CD. So coming to this, again the direction of the current is downwards, the magnetic field is this way, and the force will be in this direction, that is outwards. So let me explain it to you using this. Middle finger is in the direction of the current, forefinger is in the direction of the magnetic field, and the thumb represents the direction of the force. The force is inwards. In case of CD, the direction of current is downwards. The direction of the magnetic field is this finger, that is forefinger. It is represented by the forefinger. Then you can see the thumb is pointing outwards. Therefore, the force F2 is acting outwards and this force F1 is acting inwards. So, I will show you this in a separate diagram. Now, if you view through AD, then how these forces are going to look like. The force F1 will be acting like this and the force F2 is acting in this direction. And this is the point of axis, that is the axis of rotation. And this is the direction of the magnetic moment. Then the complete length of this is A. That is, this is the top view. If you view from this line, that is arm AD, this is how it looks like. Therefore, if AD is of length A, then this will be A by 2 and this will be A by 2. The forces are acting like this. Now you can see these forces are anti-parallel to each other. they are equal in magnitude, but their direction is opposite, and they are acting on different points. They are not acting on the same line of action, they are acting on the different line of action. Therefore, these two forces are going to form a couple and they start to rotate. They make the rectangular loop to rotate in a anti-clockwise direction. Now let us write the torque. Torque is represented by the letter tau, and torque is equal to the force into the perpendicular distance. Now the force is F1. So the torque is acting along this line. The torque is acting in this line. Therefore, I am going to find the force, the torque at this point. So the torque is given by force into the perpendicular distance. The force F1 into the perpendicular distance is A by 2 plus the force F2 into the perpendicular distance A by 2. Now you know F1 and F2 are equal and it's equal to IBB. Let us write down IBB A by 2 plus IBB A by 2. If you add them, you are going to get 2IBB A by 2. Now this 2 and this 2 gets cancelled. Torque is equal to IBB A. But what is B into A? It is nothing but the area of this rectangle. The area of the rectangle is given by A into B. Therefore, tau is now equal to IBA. The A is nothing but the area of the rectangle. So we have placed the rectangular loop in a uniform magnetic field and the magnetic field is along the plane of the loop. This is the first case. And what happened here? The force on AD and BC is equal to 0. But the force acting on this AB and CD is equal in magnitude, opposite in direction, and they are acting in the different line of action. Therefore, they are going to form a couple and they start to rotate, and it makes the rectangular loop to rotate. This is what the first case is, and the torque which is acting on this rectangular loop is equal to IBA. I is the current, B is the magnetic field, and A is the area of the rectangular loop. Now let us discuss the second case. What is the second case? Now as I told, the couple, that is the rectangular loop, has started to rotate. Now as it rotates, the magnetic field is now not acting along the plane of the loop. The magnetic field is going to make some angle with the loop, and we are going to take that as the second case. So before, the magnetic field was acting along the plane of the loop, but now the rectangular loop is rotated. Now if the rectangular loop is rotated, then it is going to make some angle theta with the plane of the loop. The magnetic field is going to make some angle theta with the plane of the loop. This is what the second case will be. Now let us discuss the case 2, where the magnetic field makes an angle with the plane of the loop. Before, the magnetic field and the plane of the loop were on the same line. But now what we have done is, we are going to make the loop to turn a bit. That is, it is making some angle with the magnetic field. So this is how the magnetic field is. Before, the loop was like this. Now the loop is going to be rotated by some angle. So the magnetic field and the plane of the loop are making an angle theta. Therefore, I have shown this here. The loop has been tilted. The loop which was like this is being rotated a bit like this. Now the magnetic field is in this direction, but the plane of the loop has been rotated a bit. Therefore, they both are going to make an angle theta. As I have told you, the dipole moment is always perpendicular to this plane. The dipole moment was in this direction. Before it was like this. Now the dipole, as you tilt this, the dipole moment also is going to get tilted. That means the dipole moment should always be acting perpendicular to the plane of the loop. Therefore the dipole moment is this, and the magnetic field is acting in this direction. In the previous case, that is in the case 1, the dipole moment and the magnetic field were perpendicular to each other. They were making angle 90 degree. So the dipole moment was acting downwards and the magnetic field was acting in this direction. Therefore they were perpendicular to each other. But now in this case, as the rectangular loop is tilted, the magnetic moment and the dipole moment are not perpendicular to each other. They are making some angle theta. Okay. So let us discuss what happens to the force due to the magnetic field on this rectangular current carrying loop. Now coming to the force on AD and BC. Force on DA, because the current is flowing from D to A and B to C. The force on DA and BC. Now let us see the direction of AD and BC. So to find the direction of these DA and BC, I am going to use the left hand Fleming's rule. So according to Fleming's left hand rule, the middle finger represents the direction of the current. So the direction of current is from D to A. So this is the direction of current and the magnetic field is in this direction. Okay. Now the direction of the force is upwards. The direction of the force you can see is upwards because the loop is being tilted a bit. It is making some angle with the magnetic field. So you can see if this is the direction of the current, this is the direction of the current, this is how the magnetic field will be. This is how the magnetic field will be. So direction of current, magnetic field, and the force will be upwards. The force is acting upwards. So I am going to take this force as some F3. Coming to the direction of BC, you can see the middle finger is pointing from B to C. What about the forefinger? It should be pointed in this direction. Therefore, let me point the forefinger in the direction of the magnetic field. The direction of the current is this B to C. Then your thumb is directed downwards. That is the direction of the force. Therefore, the force is acting downwards. This is F4. Now, these two forces F3 and F4 are acting opposite to each other and they are acting on the same line of action. Therefore, the F3 and F4 is going to get cancelled. And as you know, the magnitude of F3 and F4 will be the same because they are having length A and they are in the uniform magnetic field and the current I is flowing through them. Therefore, the magnitude of F3 and F4 will be same and they both are acting opposite to each other and the line of action is same. Therefore, F3 and F4 cancel each other. Now, even in this case, F3 and F4 are not going to act. That is, the net force of F3 and F4 is 0. Now, let us see what happens to the force on this AB and CD. So, the force on AB and CD. F is equal to IBB sine. What is the angle between this B, that is the current, and the magnetic field? It is once again 90 degree. See, before this is AB, this is magnetic field and they both are perpendicular to each other in the previous case. Now in this case, the loop is being rotated by some angle. Even though the loop is rotated by some angle, the magnetic field and the side AB are making 90 degree itself. That is, they are perpendicular to each other. Even if you rotate this by 360 degree, the angle between the magnetic field and the length vector will be 90 degree itself. That is, this AB and the magnetic field are perpendicular to each other even though the rectangular loop is rotated. Therefore, the angle here is 90 degree, sin 90 is 1. Therefore, F is equal to IBB. Thus, I am going to call it as F1. Coming to the side CD, you can see in case of side CD, I am going to take the force as F2. It is IBB same. And what about the angle? It is sine. Even the magnetic field and the length here is perpendicular to each other. Therefore, it is again 90 degree. So, I can write this as equal to F2. So, here F1 and F2 both are equal to IBB. So, till now we have seen that the forces F3 and F4, which are equal in magnitude but opposite in direction, acting on the same line of action, therefore both the forces have been cancelled. But coming to the two forces F1 and F2, they are equal in magnitude and its magnitude is equal to IBB. Now let us see what will be the direction of the forces F1 and F2 using Fleming's left hand rule. So for that, I am going to consider the case 1. In case 1, this line was along the magnetic field. So this is the magnetic field and this was the dipole moment. They both are perpendicular to each other. The force F1 was acting downwards and the force F2 was acting upwards, and they both form a couple and therefore they created a torque. Coming to the second case, in this case, what we have done is we have tilted or made the rectangular loop to rotate with some angle theta. Therefore, if this is the magnetic field, this is the magnetic field B, then the loop has been rotated with some angle theta. Therefore, the dipole moment M will be in this direction, which is making an angle theta here. So, this is how much we have rotated the rectangular loop. The force F1 will be acting downwards like this and the force F2 is acting upwards, and we know F1 and F2 are both equal in magnitude, which is equal to IBB. Next, I am now going to extend this. That is, this is the magnetic field. I will extend this like this. Now, if this is theta, this angle will be 90 minus theta. As you know, the dipole moment should always be perpendicular to this loop. Therefore, this angle will be 90 degree. If this is theta, then this will be 90 minus theta. And this angle is just vertically opposite to this. Therefore, this is 90 minus theta. This is 90 degree. Then this becomes theta. Then what about this side? This side is written as sine A by 2. As this is A by 2 and this is A by 2. This side is nothing but sine theta into A by 2. Or I can write this as A by 2 sine theta. Right? I will explain this. Because this angle is theta, the side which is opposite to this theta is nothing but opposite. That is, if I write sine theta is equal to opposite by hypotenuse. I want to find out this opposite side. Therefore, opposite is equal to hypotenuse into sine theta. What is the hypotenuse here? That is nothing but A by 2. Therefore, this is A by 2 sine theta. This opposite side is nothing but A by 2 sine theta. We know the forces F1 and F2 is equal to IBB. F1 and F2 is equal to IBB. Now let us write down what is the torque. Torque is given by the formula force F1 into the perpendicular distance. So perpendicular distance we have found, it is A by 2 sine theta plus force F2 into the perpendicular distance A by 2 sine theta. Next we know F1 and F2 are equal to IBB. So they both are equal in magnitude. And therefore, I am going to add it as 2 IBB into A by 2 sin theta. Here 2 and 2 gets cancelled. Therefore, this is equal to IB. What is B into A? AB is nothing but the area of the rectangular loop A into sin theta. And we know the dipole moment M is equal to I into A. The current we are going to represent using a capital I. Current in the rectangular loop into the area of the loop. Therefore, I into A can be written as M B sin theta. This is the torque. Or since I have this sin theta, I can write this in vector form as M cross B. So torque is equal to M cross B, where M is the dipole moment. So torque can be written as the cross product of the dipole moment and the magnetic field. So when you look at this formula, do you remember in case of electrostatics we write the torque as equal to P cross E. This is the electric dipole moment cross electric field, and that is equal to tau. And this formula is analogous to this one which we have studied in magnetostatics. So we studied that if you place a rectangular loop, current carrying rectangular loop in a magnetic field, then this current carrying rectangular loop is going to experience a torque. So it starts to make a rotation. Now if you are going to place this rectangular loop perpendicular to the magnetic field, so this is the direction of the magnetic field and you are placing this rectangular loop perpendicular to it, then the torque experienced by this rectangular loop will be 0, because the dipole moment will be in this direction. That is, the dipole moment will be along the direction of the magnetic field. So M cross B, if M and B are along the same line, what will be the angle theta? Theta will be 0 degree. Sin 0 is 0. Therefore, it will not experience, the rectangular current loop will not experience any torque if you place it in the direction, or if the dipole moment is along the direction of the magnetic field. So this is the end of the session. So in the next session, we are going to study about the magnetic dipole moment in a revolving electron. Thank you.